Orbital height determines time period. If we want a satellite to orbit the Earth in a given time period, we must place that satellite at a certain height from the centre of that field. This is why planets that are further away from the Sun have longer years. Mercury zooms around the Sun quickly compared to Earth. In the time it takes the Earth to spin 88 times on its axis, Mercury has gone once around the Sun. Venus takes 224.7 Earth days to do the same, but Mars takes 687 days. This pattern continues as you move out from the Sun. In fact, if you knew the mass of the Sun and the length of the year for each of the planets, you could work out how far out from the Sun they were following the formula r cubed equals t squared times gm over r pi squared, 4 pi squared. On Earth, the distances of our satellites are much shorter from Earth. Their distance from the Earth depends on the job they are performing. A spy satellite, which wants to see details on the surface of the planet, needs to be closer. This in turn means that it must have a greater escape velocity than satellites further out. From v equals square root of gm over r. Because the orbital distance is less than the time period, the time period is also less. Spy satellites orbit quickly and at a low orbit and cover the surface of the Earth several times a day. Typically, they follow a trajectory that covers the poles, meaning that the entire sweep of the Earth's surface spins out below it. Even in an orbit parallel to the equator, these low satellites would move around the Earth faster than the Earth spins. If you could see this type of satellite from the ground, it would appear to move away from you at some point in the day, over the horizon, and then come towards you from behind you at other parts of the day. Although you can bounce signals off these satellites, you can only do so when you can see them. For periods of the day, these satellites are hidden behind the Earth, and so out of contact with you fixed on the Earth. In order to bounce signals off satellites all the time, they need to appear in the sky all the time. In order to do this, these satellites must have orbits which are synchronized to the spin of the Earth. These satellites are called geosynchronous. The time period of a geosynchronous satellite is about 24 hours, the time period of the rotation of the Earth. This means that the satellite appears stationary in our sky, and so can be seen by large swathes of the Earth all the time. In effect, although the satellite is moving at a high speed, it is still when we look at it from the Earth. In order to achieve this geosynchronous orbit, the orbital height of these satellites needs to be much higher than the spy satellites discussed previously. The velocity of these satellites is, however, less.